let's get this clear. The more negative electrode potential. So we've got two half equations. So we've got a system. The more negative of the two half equations will release electrons. It will release electrons. Okay? If it releases electrons, if it loses electrons, then it is oxidized, and it will reduce the oxidized form of the system with the more positive electrode potential. Now, all of this sounds a little bit kind of academic, but you've got to practice these things, okay? It's two possible ways around to have it. You've got to make sure you get it the right way around. So let's take a system that we're very familiar with. So the displacement of halide ions by halogens. Okay? So we know, obviously, that, or we've always known, forever and ever, that chlorine will displace iodide. Chlorine will become chloride and iodide will become iodine. We know that. And that fits with our new knowledge, doesn't it? The more negative, here we go, that's more negative, believe it or not, will release electrons. Its tendency is to go to the left. And the more positive will accept electrons. Okay? So we kind of know that's a feasible reaction. Yeah? Good. And the anti-clockwise rule reinforces that. And there's quite a big difference between the electrode potentials. So the E cell here would be, or what would it be? Quickly doing the maths, it's going to be 0.82 volts, isn't it? Which is relatively large. So we would expect this reaction to be feasible. It is feasible. We'd expect it to happen spontaneously. Okay, we would expect it to happen. So the general method, this is where we get back to the idea that you have to develop your own system for doing these kind of questions. Will chlorine gas oxidize iodide ions? And we look at the electrode potentials. This is more positive, so this accepts electrons, and this is more negative, so this releases electrons. So yes, essentially. Will the opposite process occur? So you might get this question in an exam, and you'd have to say, well, will iodine oxidize chloride ions? Well, no, because given the electrode potentials, because it's the more negative, it's more likely to release electrons, and the chlorine is more likely to accept electrons. So the reverse process is not feasible. Okay, at this point we could also start talking about the difference in the SEPs, the idea that the greater that difference, the more likely the reaction is to happen. Okay, it's like a driving force for the reaction. We'll talk about this more because we have to bring in Gibbs free energy, and we have to bring in entropy, and we have to also bring in equilibrium constants. We'll talk about that. We'll try and bring the whole thing together. A feasible reaction, so if we've determined that a reaction is feasible, then it might not happen. There are possible situations where the reaction, even though it looks feasible, it doesn't happen. And we have to consider why that might be the case. So here, for example, if we look at the energetics of a reaction, we might find out that the reaction is thermodynamically favored and that the reaction should happen. But the kinetics of a reaction, activation energy, is an important factor. So energetics can say whether it's feasible, whether it should happen, but kinetics will determine the rate. And the rate may be very, very low. It may be insignificant. Okay, so let's have a look at examples of this. Now this is a combination of two half cells, half equations that we will kind of have come across before. You know that copper metal does not react with hydrogen ions. Copper is unreactive in dilute acid, isn't it? Okay. Right. Now we know why. And look at this. What's the natural tendency here? It's for the hydrogen to become hydrogen ions and for the copper ions to become copper. So the natural tendency is opposite to the copper reacting with hydrogen ions. The more negative of the two electrode potentials will release electrons. The more positive will accept. Okay, that's good. However, this system implies that copper ions should be reduced and that hydrogens should produce hydrogen ions. Okay? But it doesn't happen under standard conditions. Even though thermodynamically it looks like it should happen, it doesn't. Why? Well, it's the strong covalent bond in the hydrogen molecules that resists being broken. And because that resists being broken, then the reaction cannot proceed. So even though there's a difference of 0.34 volts in the standard electrode potentials, here the activation energy is too high. Okay. Second reason, conditions may not be standard, and that affects the position of equilibrium. Okay, so what conditions? Change in concentration, temperature, and pressure, and you can actually shift equilibria, as you know. Okay, so you might actually change the electrode potentials. They won't be standard anymore, but the electrode potential will change according to these conditions, and it means a reaction may proceed in a direction you weren't expecting. So let's have a look at this system. We make chlorine gas in the lab using manganese 4 oxide and concentrated hydrochloric acid. Now let's look at these systems first. This is the more negative of the two values, so we'd expect this to go to the left, releasing electrons, and this to go to the right. So that implies that in this system, chlorine gas should not be produced. In fact, chlorine gas should be used up to make chloride ions. There you go. That's the spontaneous tendency. But if that were the case, we couldn't make chlorine gas using this particular system. What are we changing? Well, the clue is here. Look, the concentrated hydrochloric acid changes this. Why? Well, let's have a look. If I increase the concentration of the chloride ions, which way is this equilibrium going to shift? To the left. And if I increase the concentration of hydrogen ions, which way is this equilibrium going to shift? To the right. Okay, so by increasing the concentration here of the hydrochloric acid, we cause the equilibrium, or we cause the system to shift in a direction we weren't expecting. So here the conditions aren't standard. The increase in the chloride ion concentration shifts the bottom equilibrium to the left and the top equilibrium to the right. And chlorine gas is produced. It is produced. Let's continue with this system a second. The changes in concentration affect the electrode potentials. So if we increase the hydrogen ion concentration in the top equilibrium, then it makes it more likely to go to the right to accept electrons. This would make the electrode potential more positive. Okay? Let's just get that clear a second. As we go down the table, the electrode potentials become more positive. It's more likely that things will accept electrons. So this makes this number more positive. It goes in this direction. Increasing the chloride ion concentration makes the equilibrium shift to the left, and that makes this number more negative. So at some point these numbers will cross, and the reverse reaction to the one that we would expect starts to occur. Okay? Other factors that may affect this situation: if a gas escapes from the system, as is the case here, then you know if the gas is escaping, if this is leaving the system, then this equilibrium will shift in that direction. So gases can be important. Temperature will affect the position of equilibrium. We're very clear about that. That makes sense. Right, disproportionation reactions. Disproportionation, remember, is when an element is both oxidized and reduced in the same reaction. So copper 1 ions, they're not stable under standard conditions. These are the electrode potentials. So if you look at this, this is more negative, this is more positive. So it's more likely that copper 1 will become copper 2 and the copper 1 would become copper. And that's combined in this equation, and then the E cell for these two would be that. So this is the feasible reaction. We can predict this reaction will take place. Okay. We can do the same thing using iron to see if iron 2 will disproportionate. Here we prove that copper 1 will disproportionate. It's energetically favored, thermodynamically favored. But will iron 2? So there's iron 2 there in equilibrium with iron metal, and there's iron 3 in equilibrium with iron 2. You can probably see straight away the likely change in these equilibria, the spontaneous change if they're in contact with each other. The top will shift to the left, the bottom will shift to the right, and iron 2 ions would be produced. You can combine those equations if you want to, but you can see that it's much more likely that iron 2 is produced if these two systems are combined. Okay, if iron 2 is being produced, then obviously it's not disproportionating, it's the reverse. So iron 2, in standard conditions, the iron 2 oxidation state would be more stable. Entropy and cells. So this is the equation. You might as well learn it. Gibbs free energy is minus NFE. What do they mean? N is the number of moles transferred in the reaction, number of moles of electrons, transferred in the reaction, and F is the Faraday constant, which you'll always be given. Don't worry about that. Okay, so let's have a little look just to summarize this. If E cell is positive, delta G is negative, so the reaction is spontaneous. If E cell is negative, delta G would be positive, so it wouldn't be spontaneous. And if E cell is 0, delta G is going to approach 0. The reaction can be at equilibrium. It can reach an equilibrium. Intuition will also tell us that the size of E cell, the difference in the electrode potentials of the two half cells, the bigger that is, then the bigger the entropy change. That's intuitive, isn't it? Okay, so if we've got this relationship up here, we also know, thinking about entropy, total entropy, when we went from total entropy to Gibbs free energy, we multiplied by minus T. So to go back, we would have to divide the above expression by minus T. Now, if you're stuck with that, go back to your work on entropy that we did. So we get delta S tot is NFE over T. And this clearly shows us that the total entropy change in a reaction is proportional to E cell. The bigger the E cell, the bigger the entropy change, and vice versa. And now let's look at equilibrium constants in cells. So we've got delta G is minus NFE. We saw in the last topic, this is the equilibrium constant, isn't it? So delta G is minus RT ln K. So you can see what we're going to do here. We're going to derive the relationship between ln K and the E cell. And what does it end up being? You can have a play around with that mathematically if you want. They are the two expressions. So ln K becomes NF E cell over RT. Again, ln K is proportional to E cell. Makes sense. The greater the E cell, the greater the K. The further to the right the reaction will go. Okay. the little equations and manipulations you need to be able to do. Okay, right. Read the pages indicated, try all the questions you come across, and let this soak in. There's a lot of equations and potential calculations you could do here, so take your time.